Hopefully, I remember everything that I intended to say. Um, had a parent-teacher conference this morning at 7, and then we had a meeting um, between my first class and this class. So I haven't had a chance to look at the slides since yesterday. So we'll see what I can remember. Okay. So after this week is over, we have, 4 more weeks left in the semester. And I'll be thinking about the final project for this class and also about written exam number 2. Um, okay. So, yeah, all right. So why don't we get started? Please make sure you have been keeping up with the reading. It's not a lot of pages, and so a little bit a day will bring you far. And I fully expect that you might need to consult other resources to help you with the material in the book. Certainly, the slides are there. I didn't get a chance last night to post the screencasts. Had to get some other stuff done. Okay, so when we last left off, we talked about the following video, and this video is a view of instrumentation of the number of people entering a retail establishment. And so we have an overhead camera, and this overhead camera is tracking people who leave the establishment and people who leave the establishment. And the difference between the two is the number of people in the store. Now, certainly for the till or the register, you can also associate the number of people in the store with the amount of revenue per unit time and talk about the most profitable parts of your day. And then, given these units of time, delta t, pose a Poisson distribution, and then use that in simulations to answer questions about revenue and the number of employees that you can afford to have on staff at a given time while still making your profit targets. Okay, and so last time we talked about the Poisson, and in talking about the Poisson, we began with this really weird binomial distribution, and this weird binomial distribution had some number of trials n that was infinite, and it corresponding to continuously flipping a coin again and again and again every moment in time in infinity. And so we took that binomial and the probability mass function for it, and we let the limit for n, the number of trials, go to infinity, and we came upon an expression for the Poisson mass function, and we showed using the Maclaurin series that the law of total probability holds true for the Poisson in that the sum of these Poisson probabilities for a Poisson probability expression across all values of x, the number of events observed, sums to 1. Okay, and we made use of the Maclaurin series in order to do that. Any questions about this? Okay, let's continue on. And so proving the law of total probability very often is not enough. You also need to show or prove the summary statistics. And for the Poisson, we're going to show the mean and the variance. And what you'll find is that the mean and the variance for the Poisson are going to be the same thing. But that's not the case for other distributions. Okay, so let's take a look first at the mean. And I've budgeted for lots of questions, so who knows, we might get out earlier, we might get out on time, depending on the questions, so try to anticipate. All right, so we know the distribution for the Poisson, p of x e to the minus lambda times lambda to the x upon x factorial. And this is our probability mass function. We called it a mass function because this is a discrete distribution. And to jar your memory, discrete means that the quantity of interest is countable. In this case, we're interested in the number of events that we observe. The probability that the number of events observed is x, and that's what that mass function measures. And therefore, the number of events we can observe can be 0, 1, 2, 3, so forth. And because it's countable, this is a discrete distribution. And for discrete distributions, the probability is called a mass function. And we'll contrast that with continuous probabilities, those traffic and quantities that are uncountably infinite. We call those density functions. Okay, so we will prove that the rate lambda is equal to the mean or the expectation of a Poisson random variable. So we have our expression for what the expectation is. It's the probabilistic sum, and that is the value x, where x is the number of observed events at some moment in time. Be that customers that arrive in the store, could be routers arriving, packets arriving at a router, and so forth. And we produce the weighted sum, so we multiply each x times its probability, where the probability mass function we use is this expression that we proved last time for the Poisson distribution. And so computing this expectation is E of x, and we can also summarize that with Greek letter mu. And so we're just substituting now for what expectation is. We say x times p of x, the weighted sum for x goes from 0 to infinity. And so we substitute for p of x, we substitute the probability mass function. So we're substituting here x, we multiply, instead of by p of x, we multiply by e to the minus lambda times lambda to the x upon x factorial. So there's our substitution. So now we're just going to make a couple manipulations using algebra, and we'll arrive upon that expression. And then again here, we're going to make use of the Maclaurin series, in this case for E of x, and we're going to make that substitution using that to arrive upon our answer. Okay, so we have this e to the minus lambda, and you'll notice here this e to the minus lambda power, that term does not involve x. So it is a free variable underneath that summation, and for all intents and purposes, it looks like a constant because it does not involve this x. So we can take advantage of the law of the distributive law of multiplication over addition and factor out this e to the minus lambda out from under this summation for each of these terms in the sum. So we bring that out front and we write e to the minus lambda times the infinite sum for x goes from 0 to infinity, and we're left with the other terms that do involve x times lambda to the x upon x factorial. Okay, so now we're going to take a look at this expression, and we'll make another observation here. And so this observation is we see this x factorial in the denominator. And let me get my marker here. Since I'm having issues with connectivity and the pen and the tablet, I'll just do it old school on the board. And so when we have or write x factorial, expanding out the definition for x factorial, that's nothing more than x times x minus 1 times x minus 2 dot 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 times 2 times 1, right? And so if we take these bottom terms here for the x factorial, we can write these bottom terms as x minus 1 quantity factorial, right? Because a factorial is just the successive multiplication of terms up to and including that x. So we can rewrite that x factorial as x times x minus 1 quantity factorial. It's the same thing, right? Based on the definition of what x factorial is. So if we do that, we look at this term here. We had already brought out our e to the minus lambda out from underneath the summation, right? So if we take our x and we take our lambda to the x, and we rewrite our denominator x factorial as x times x minus 1 quantity factorial, we essentially peel off that x term in the factorial, and we can now use that to cancel that leading x that we have out front of this expression. Okay, so we do that, and we then cancel that x in the numerator with that x in the denominator that goes to 1, and we're left with that lambda to the x power upon x minus 1 quantity factorial. Any questions about this? Does that make sense? Okay. So if we do that, we're now left with an expression, kind of jumping steps here. We're left with an expression that looks like the following. We're left with e to the minus lambda, right, our leading term, and we have our summation, x goes from 0 to infinity, of lambda to the x power over x minus 1 quantity factorial. Now, an observation we can make here is that if we substitute, let's see, what did I do? Okay, I didn't cancel it yet. All right. Let me go back and start over. All right, so I did that factoring. I have my x goes from 0 to infinity. I factored out my e to the minus lambda. I have my leading x, and I have my lambda to the x power, and then I factored out from the x factorial, I took out that x, and I'm left with x minus 1 quantity factorial. Okay, so let me pick back up from there. I apologize for that. So in this case, if I take a look at this expression here, the summation part, let me try unrolling this summation one term at a time. Now, if I unroll this summation, I can rewrite that as the sum, right? Because that's what summation means. But I can start here by evaluating the x equals 0 term, right? If I evaluate the x equals 0 term in the summation, I'm basically adding that to the remainder of my summation for x equals 1 on through infinity of that x lambda to the x over x times x minus 1 quantity factorial. So for that x equals 0 term, what do I have? I have x here, a leading x, and I'm multiplying that times this other stuff. It doesn't matter what the other stuff is. And so for x equals 0, well, this term is a 0, and 0 times anything is 0, right? So essentially, for x equals 0 term for the summation, the first term is always going to be 0. So I can rewrite this expression as the following expression, taking the index from x equals 1 to infinity instead of x equals 0 to infinity. Okay, so I'm basically evaluating that first term of the sum. Okay, make sense? Any questions? Yes. Great question. Because even though I have here x equals 0, right? So that was my x. And then I have lambda to the x, lambda to the 0, right? Over 0 times 0 minus 1 factorial, which kind of doesn't make sense, right? And yes, this should be infinite, right? So if you imagine this is infinity, it still applies 0 times anything is 0. It doesn't matter what you're multiplying by. 0 times anything is 0. Right? That's by definition of what 0 means. And so it's convenient that while, yes, if I have 0 in the denominator, this should be infinity, but 0 times anything is always 0. It doesn't matter what I multiply by. So I'm just using that fact conveniently to make life simple. Okay? Great question. Any other questions? No? No? All right. So let me erase that. So I have this expression, and so I can peel off, didn't mean to do that. I can peel off that x equals 0 term from the summation, and that allows me to rewrite the rest of the sum, taking my index from x equals 1 to infinity instead of x equals 0 to infinity. Okay, so now I take that expression, right, x equals 1 to infinity, and I'll just kind of get rid of that 0 term just because it's hanging around. I do that for pedantic reasons, just so you'll see what I did. I always used to hate as an undergrad, why didn't they show the step? So I like to show the step. And this is what I'm left with. E to the minus lambda, the infinite sum from x goes from 1 to infinity of lambda to the x over x minus 1 quantity factorial. So now I'm going to make a few observations. I want to kind of clean this up because I want to make it look like a Taylor series, and I want to make life simpler. And so I look at a pattern and I say, gosh, well, to make this a Taylor series, I kind of need to have the thing that's factorial look a lot like the exponent, right? But this exponent here is x, and that factorial thing says x minus 1. So one way I can kind of make it look nicer is I can take my lambda to the x power, and lambda to the x power is nothing more than lambda times lambda x many times, right? So I can certainly say, okay, let me take one of the lambdas, and I'm going to keep x minus 1 of those products of lambda with itself together. And I can rewrite my lambda to the x power as lambda times lambda to the x minus 1 power because the exponents add, right? This is a 1 exponent. That's just lambda to the x minus 1 plus 1 power, which is lambda to the x power. Okay, so I'm going to factor out one of these lambdas from that lambda to the x, and that's going to put it in a nice form that's going to look more and more like a Taylor Maclaurin series that I can use to reduce this. Okay, so I'm going to do that. So I do that, and I have e to the minus lambda. That hasn't changed. That was that term that I factored out because it's a free variable. It does not involve that x index for the summation. And then I factor out that single copy of lambda, lambda to the 1 power, and I have lambda times lambda to the x minus 1 upon x minus 1 quantity factorial. Okay, does that make sense? Okay, so now I say, okay, gosh, well, to be a Maclaurin series, the sum has to be from 0 to infinity, not from 1 to infinity. So I need to figure out a way to make that from 0 to infinity. Well, how am I going to do that? Well, I can do that by changing the variable. I'm going to change that variable from x to something I call y, and y is just going to be 1 less than x. Y is equal to x minus 1. So everywhere I see an x minus 1, I'm going to write y in its place. And if x equals 1, I'm going to write y's equivalent, which is x minus 1, so y is going to start from 0. So we're going to do that and do a little bit more cleanup to put this in a form that looks much nicer, that can be expressed directly, that we recognize as a Maclaurin series. So I started out and I factored out that lambda. So my exponent went from lambda to the x to lambda to the x minus 1. And guess what? Conveniently, this lambda, it no longer involves x, that leading lambda. And so that looks like a constant. It doesn't involve x. So I can also factor out this multiplied by lambda. So I do that, and I bring that lambda out from the summation. I have lambda times e to the minus lambda, and I'm left under the summation for x goes from 1 to infinity of lambda to the x minus 1 upon x minus 1 quantity factorial. Does that make sense? So this is factoring out a lambda. That single lambda becomes a constant, and I can factor that out. Okay. So I do that, and now I'm going to say let this new variable I call y equal to x minus 1. So y is equal to x minus 1. And I have my lambda e to the minus lambda, my summation. And it started out as being x equals 1 to infinity. And I had lambda to the x minus 1 in the numerator originally, and x minus 1 quantity factorial in the denominator. So, okay, well, everywhere I see x minus 1, I say y, right? Well, I've seen x minus 1 here, so I'm going to rename that y. I have an x1 minus 1 here. I'm going to rename that y, so I have a y factorial. And then here, if I want to change this to y, I have to look at the value. So if I want to change this x to a y, I have to take x's value and subtract 1, right? Well, this is a 1. To be a y, I have to subtract 1, so that now goes to 0. Now, of course, the upper bound of the index for the summation, well, if x is equal to infinity, y is equal to x minus 1. So if I want to change this to y, I subtract 1 from that to call that y. Well, infinity minus 1 is just infinity, right? Okay, so the top bound of the summation becomes infinity, and the bottom bound is equal to 0. Does that make sense? So I'm just changing variable and from x to y, and I'm just propagating the result of that change to update my equation. So now I look at this, and I said, wait a minute, that looks a lot like a Maclaurin series, and it is actually a Maclaurin series. That's the Maclaurin series for e to the lambda. And so let's harken back to what a Maclaurin series is. A Maclaurin series has 3 parts. It's a sum for x goes from 0 to infinity. It has a derivative portion, so d, let me see, k. The kth derivative with respect to x of our function f of x, and you evaluate that kth derivative at 0, right? You have a factorial component, k factorial, and then you have a polynomial component, uh, x to the k power. Okay, there we go. When the font is really big in front of you, it's harder to see it than when it's on paper. Okay, so if our function f of x is equal to e to the x, well, d dx of e to the x, that's just e to the x, right? If I take the second derivative, so let's call that the first derivative, the second derivative, d to dx of e to the x, right? That's just the derivative of the result of the first derivative. That derivative is just e to the x, right? So the derivative of any order for e to the x is just e to the x. If I evaluate that derivative at 0, if I evaluate this at 0, that's e to the 0, which is just 1. If I evaluate this at 0, e to the 0 is just 1. So the derivative portion for e to the x is just 1 in all cases for the kth order derivative. So if I look at the rest of it, well, I have the factorial term and I have the polynomial term. And that's exactly what I have here. So I can take this infinite sum going from 0 to infinity of a polynomial term over the factorial term and rewrite that as e to the exponent, where the exponent here is this base that I'm raising to some power. Does that make sense? Any questions about this? It's a direct application substituting the Maclaurin series for e to the x. And here we've covered what the kth order derivative is for e to the x. It's just evaluated as 0. It's just 1 in every case. Okay. So when I see this expression, I say, okay, well, knowing that this is the Maclaurin series for e to the lambda, I'm just going to replace that sum, this portion, with e to the lambda. And so now I have an expression that leading lambda times e to the minus lambda. I now substituted for the Maclaurin series here. I've substituted e to the lambda. And now my e to the lambda cancels with that e to the minus lambda, goes to 1. Okay? And I'm left with lambda, which is exactly what I was trying to prove. So the expectation of a Poisson random variable with an average rate lambda is just lambda. It kind of makes sense. It's obvious, right? But you still have to prove it. Any questions about this? Does that make sense? No questions? Okay. So let's move on to the variance. The variance talks about the dispersion, or the spread, if you will, for values for that random variable. And we'll show that the variance of a Poisson distribution is also lambda. So let's go back to the definition of what variance is. Variance, summarized by Greek letter sigma squared, is the expectation for which the variable's value x differs from its mean squared, because you care about the magnitude but not the direction, and you're taking that weighted sum for that dispersion, right? So we take x minus mu, quantity squared, we square it, and then we weight that by p of x, where p of x is a probability mass function for the Poisson e to the minus lambda times lambda to the x upon x factorial. Okay, so we can use something called the variance equation. I'll take a segue for a moment and actually prove the variance equation. If you want to compute this variance, e of x minus mu quantity squared, that's nothing more than the expectation of x squared minus the expectation quantity squared. And that comes from the definition of variance, and it's a popular substitution or identity that's used all over. So let's take a look at what variance is. We said variance of x, more generally, is the sum for all values of x, x minus e of x, quantity squared, times p of x. Okay, so we'll take this expression and we're going to do the square and distribute the multiplication by p of x over the result of this square, right? So we have x squared minus 2 uh, e of x times x plus e of x quantity squared times probability of x, right? So I just applied the FOIL rule, the first term squared plus the second term squared plus 2 times the cross term, right? All right, so now I still have my summation, right? And now I'm going to distribute that multiply by p of x time with each of these terms. So if I do that, and I'm going to then take each term and then separate them out. So I'm going to sum together the first term, subtract the sum of the second term, subtract the sum of the third term. So let's do that all in one fell swoop, right? So I'm going to multiply p of x times each of these terms, and then I'm going to take the resulting sum and separate them out. Okay, so the first one is the distributive rule, distributing a multiplication over addition, and then the next one is the associative rule. I'm re-associating those summations. So that'll give me the sum for all x's, and I have x squared times p of x. That's my first term. And then I have minus the sum over all x's of 2e of x times probability of x. And then I have plus the sum over all x's, e of x quantity squared times p of x. Any questions about this step? So I'm just kind of doing two steps in one. I'm first multiplying p of x times each of these terms, and then I have my single sum. I'm going to associate this term, those sum together, this term, and that term. All right, so I just did it in one step. Okay. Any questions? That make sense? Yes. All right. So now I make some observations. Okay. Well, let's start with the first term. So this first term here, I have an x squared p of x. Oh, that's nothing more than the expectation of x squared, right? Expectation of x squared, I take this quantity and I do the weighted sum with the probability of x. That's exactly e of x squared. Okay, so let's look at this last term. So this last term, when you compute an expectation, that's a value we called mu, right? Now mu as a value, it doesn't change underneath the summation. If I square mu squared, it doesn't change. It looks like a constant. Yes, I say e of x, but e of x is a quantity. So this e of x as a constant, e of x squared, because it's a constant, I can move it out from underneath the summation, and that becomes plus e of x, which is a constant, quantity squared, times the sum over all x times probability of x. I could have also taken my e of x and just rewritten that e of x squared as mu squared, right, to make it look nicer, right? But I'm going to put it back to e of x squared because I want to get back this variance equation, e of x squared. Okay, so with this third term, I'm not done yet. And I make an observation, and if I look at that summation, I have the summation of p of x with itself for all values of x. Well, law of total probability says, okay, if I sum a probability over all values of x for that probability, I get 1. So this term here, that summation goes to 1, and so I'm left with e of x squared. So I'll just write e of x, the expectation mu, quantity squared. Okay. So now let's look at this middle term. Now, I just got done saying that an expectation is a constant, mu, right? It's exactly what it is. I have a 2 times something that's a constant. 2 is a constant, and mu, which is also e of x, is also a constant. So I can bring these two constants outside of that summation. So I can rewrite this as minus 2 expectation of x, summation over all x, x times p of x. Okay, I make another observation. Wait a minute. This x times p of x, that's exactly the definition for what expectation of x is. So I'll rewrite that term as expectation of x. So now for the second term, I have 2 times the expectation times another expectation. That's nothing more than minus 2 expectation quantity squared. You multiply something by itself, it's squared. So if I look at these terms, I wish I had another board, I have e of x squared minus 2 copies of e of x quantity squared plus 1 copy of e of x quantity squared. So I have minus 2 of something plus 1 of something. That's just the same as minus e of x quantity squared. Does that make sense? So I could call e of x quantity squared, I could call that mu squared, call that 2 mu squared, and I call this mu squared. If I said 2 mu squared plus mu squared, that's just minus mu squared, right? And this is my result. So I put those two together, and I'll put them together up here. Really wish I had another board. And I'm left with variance of x, that's what I started with, is equal to e of x squared minus the quantity e of x, which is the same as mu, squared, right? And so there's exactly my variance equation. So whenever you want to compute the variance, you could compute the variance directly by saying x minus mu quantity squared times p of x, or you could go through all those manipulations and use the following identity, which is called the variance equation. Any questions about this? Does that make sense? Okay. And so I really wanted to use the digital pen to do that, but having a lot of issues with connectivity between the tablet and the laptop. I have to figure that out at some point. Okay, so we're going to use this variance equation, and we're going to use this to derive the expression for the variance of the Poisson distribution. Okay, so we do have one of the pieces. We just got done on the previous slide proving that the mean, or E of x, for the Poisson, or mu, is equal to lambda. So if we're going to use this variance equation, we already know what this E of x quantity squared is. Well, E of x is equal to lambda, quantity squared makes it lambda squared. So we're kind of halfway there with the variance of a Poisson distribution. That's why the variance equation is useful. Because once you solve the mean, you're halfway there. You just have to compute E of x squared. Okay? So now let's do that. So we have the variance equation, and we just demonstrated where it comes from. And we know that we have an expression for this half of the variance equation because we know E of x is equal to lambda for a Poisson variable. So now we're going to look at the other part, this E of x squared. Okay, so you know that E of x is equal to lambda. So now we're going to show the E of x squared here, right? So we're just going to do a substitution. So E of some expression, and let me write it in general terms and then show it what I have on the slide. If you have the expectation of any function of x that's equal to that value of the function times the probability of x. So if my function is x squared, right, to find the expectation of x squared, that's just x squared times the probability of x. It doesn't matter what that function is, okay? So I plug that in for the Poisson. And for the Poisson, we know the probability mass function is e to the minus lambda, lambda to the x over x factorial. Okay, so I'm going to make that substitution for p of x, and I'm going to write x squared times p of x, and that gives me the following expression. Here's my infinite sum over all values of x. And so the values of x, when you're talking about the number of observations of the occurrence of some event, you can have 0 observation, you can have 1 event observed, 2, 3, 4, and so forth. So we have this infinite sum, x goes from 0 to infinity. When we compute our e of x squared, there's our x squared, and there's our p of x, the mass function for the Poisson. Okay, so now we're going to do a little bit of manipulation and sort of tell you the answer up front, is that we're going to make use of the Maclaurin series again to reduce this for us. Okay, all right, so what are we going to do? So one of the problems is that we want to cancel this leading x squared, but it's a little bit problematic, and it's problematic because it's an x squared, but we have an x factorial in the denominator, right? So we're going to do something a little bit different to help us out along the way, because we want to kind of morph this thing into something that looks like a Maclaurin series, so we can ultimately cancel out this e to the minus lambda with something else that looks like e to the lambda. Okay? All right. Any questions so far? Make sense? Okay. So let's do that. So what we're going to do then is, instead of e of x squared, we're going to compute e of x times x minus 1 and then kind of fix up the difference. And the reason why we're going to do it with this e of x times x minus 1 is because when we look at this expression, we see an x factorial, and we can get an x times x minus 1 there, right? So instead of solving for e of x squared, that term, we're going to solve for something that's kind of close to e of x squared, right? And this e of x times x minus 1 is close enough, and we're going to fix up the difference, okay? So if we take this expectation instead of e of x squared for that part of it, we already know e of x is lambda, so we're halfway there with the variance equation. But instead of e of x squared for the first part of the variance equation, we're going to do e of x times x minus 1, okay? So if we take this term here for which we're taking the expectation, that new term, x times x minus 1, we just multiply x minus 1 by x, and we have e of x squared minus x. Okay, so we're going to work through this e of x squared minus x, and then go through a bunch of other manipulations that's going to get us to a solution. Okay, so let's take this e of x squared, x times x minus 1. So we plug in for expectation. So there's my function, x times x minus 1. That's what I'm taking my expectation over. And we multiply by the probability for the Poisson. So it's a weighted sum. So here, my probability is e to the minus lambda times lambda to the x upon x factorial. Okay, so given that, now we're going to take a look at this summation. We're going to kind of peel off the 0th term when x equals 0, and we're going to peel off the first term when x equals 1 and make a few observations. So when x equals 0, what happens? Well, when x equals 0, this is 0, and it doesn't matter what everything else is, right? 0 times anything is always 0. So for x equals 0, that summation is evaluated at 0. Likewise, for this summation, when x equals 1, well, this middle term, 1 minus 1 is 0. So the value of this term, as this sum, is 0 for both of those cases. So we're going to take our summation, x equals 0 to infinity, of x times x minus 1, e to the minus lambda, lambda to the x over x factorial. And we're going to substitute for x equals 0. Well, we get 0 times whatever, it doesn't matter, so 0, plus the term for x equals 1. Well, this term is 0, so the whole term ends up as 0, plus the remainder of that sum, x equals 2 to infinity, of x times x minus 1, e to the minus lambda, lambda to the x over x factorial. So we're essentially going to strike out the 0th term and the first term from the sum just by using algebra and the identity that you multiply anything by 0 and it's 0. Okay? Any questions about that? Now, as long as the mathematical manipulations you make are valid, right? You haven't violated any rules, and it's the same expression. It's just the first two terms of the sum don't contribute anything. Okay. No questions? Make sense? All right. So we can rewrite it thusly. So after that manipulation, now we've changed the bottom index of our summation because for x equals 0 and x equals 1, it equals to 0 anyways. So we just rewrite it this way, and we haven't violated or broken any rules. All right. So now we're going to make another manipulation. We're kind of almost there in making this look like a Maclaurin series, but we need to do a little bit more work for what this Maclaurin series is ultimately going to look like. There are a couple things that we worry about. For the Maclaurin series, remember, the bottom index of that summation to be a Maclaurin series has to be 0. So we have to find a way to get this to be 0. We can do that through a change of variable. And then we also have to kind of work with the exponents here and get rid of that e to the minus lambda, which just happens to be a constant anyways underneath the summation. It does not involve x anywhere, right? This e to the minus lambda. So let's take a look at what we're going to do. So if we take our x factorial and we take the definition of what factorial means, well, x factorial is x times x minus 1 times x minus 2 times x minus 3 dot 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 eventually times 2 times 1. Well, if we just group together these multiplications, that's just x minus 2 factorial. And we can just multiply those two terms. We say x times x minus 1 times x minus 2 factorial. So we can rewrite what our x factorial looks like. And we do that on purpose because we see that this s factorial is in the denominator, and we want to cancel that confounding x and x minus 1 in the numerator. Make sense? All right. So we do that, and we get the following expression. So we have an x minus 1 here, numerator. We have an x minus 1 there in the denominator. So the x in the numerator and denominator goes to 1. Likewise, bless you, the x and the x minus 1 in the numerator and the x minus 1 in the denominator also go to 1. So we're left with this expression, e to the minus lambda. That hasn't gone anywhere. And the remainder here, we have lambda to the x over now x minus 2 quantity factorial. Okay, so we're just doing a little canceling, and we're also looking at the definition of what factorial is to reduce this expression. Okay, so now we see, okay, well, we have an x minus 2, we have an x equals 2 there. We can certainly factor out this e to the minus lambda, but this is kind of funky here. This exponent needs to be a little bit different, right? So what we're going to do, I'll just kind of rewrite that again to put it up there. We're going to factor out that e to the minus lambda because it doesn't involve x anywhere. And because it doesn't involve x anywhere, it looks like a constant. And we're taking advantage of the dual, if you will, of distributive rule for multiplication over addition. And we're factoring out this e to the minus lambda. It looks like a constant because it doesn't involve x anywhere in e to the minus lambda. So we bring out e to the minus lambda in front of our summation. We're left with, under that summation, lambda to the x over x minus 2 quantity factorial. So now we can actually start peeling off some of these lambdas. Again, lambda to the x power is nothing more than lambda times lambda times lambda times lambda x many times, right? So if I take the last x minus 2 lambdas multiplied by itself, that's just lambda to the x minus 2 power, but I have these leading multiplications of lambda times lambda out here that I'll keep around, right? So if I do that, I factor out lambda times lambda from this lambda to the x, and that leaves me with lambda squared, right? Because that's what lambda times lambda is, times the rest of these lambdas multiplied with one another. They're x minus 2 many of them. So I get lambda to the x minus 2 power. Okay, so everything else is the same. I still have that denominator, x minus 2 quantity factorial. Does that make sense? So I'm just looking at the definition of what exponent means, and I'm just associating the multiplications with one another for these lambdas differently. Okay, so now this is where it starts to look even more and more like a Maclaurin series. Now, I take this lambda squared that's inside the summation. That lambda squared does not involve x. It looks like a trick, but no, it's not a trick. It's just rules of mathematics. This lambda squared is a constant, doesn't involve x anywhere. So it looks like a constant underneath that summation. So now I can factor this out from underneath that summation. So I do that, and I get a lambda squared times e to the minus lambda, and I have my summation, lambda to the x minus 2 over x minus 2 quantity factorial. Okay, so that's just a little bit of algebra still. And it's starting to look more and more like a Maclaurin series, but the biggest problem is that this index on the summation has to start from 0 to be a summation. And moreover, the factorial kind of needs to look like the exponent on the variable here, lambda. And it kind of does, right? I have x minus 2 factorial. I have lambda to the x minus 2. So let's now make a substitution. We're going to do a change of variable. We're going to say let y equal x minus 2. So if we let y equal x minus 2, right, that means everywhere I see x minus 2, I'm going to replace that with y. I have x minus 2 here, so I'm going to replace that with y, and that becomes lambda to the y. I have x minus 2 for the factorial part of our Maclaurin series, so I'm going to replace that with y, and it becomes y factorial. And then I'm going to replace this x with y. So if I have a y that I turn an x into, I have to subtract 2, right? So here I'm going to write y equals 0. Now, of course, the upper bound of the summation, that's going to be infinity minus 2, but infinity minus 2 is still infinity, right? So I make those substitutions with my change of variable, and now I have lambda squared, e to the minus lambda, summation, y goes from 0 to infinity, of now lambda to the y, y factorial upon y factorial. That is exactly the Maclaurin series for e to the lambda. Okay. Again, if you take the kth derivative of e to the x, it's e to the x, right? And so this looks like e to the x, right? That kth derivative or the yth derivative evaluated at 0, right? So if the derivative of e to the x is always e to the x, evaluated at 0, it's 1. So all I'm left with is the polynomial term, lambda to the y, and the factorial term, y factorial, 1 over y factorial. So this is exactly the Maclaurin series for e to the lambda. So I replace this Maclaurin series, right, with e to the lambda. So there's this replacement. And I have lambda squared times e to the minus lambda times e to the lambda. And that's just lambda squared. E to the minus lambda times e to the lambda goes to 1. So I have an expression now, lambda squared, and that's an expression for the expectation of x times quantity x minus 1, right? So I'm going to use that result. For any questions about this? So really, it's all just algebra at this juncture, right? Which just also says how important algebra is in general across disciplines. But nonetheless, I have an expression, lambda squared, and this is the result of taking the expectation of x times x minus 1. Now, of course, our whole goal at the outset was trying to make it easier to do the variance equation, where the variance equation said the variance of x is equal to e to the x squared minus e of x quantity squared. And we already proved that e of x is equal to lambda, so we say minus lambda squared. And we said that this was too difficult to compute, so instead of computing that, we're going to do e of x times x minus 1 in its place, and we just shown that this expectation is lambda squared. So let's go forward with what our final few manipulations are. Okay, so we have an expression for e of x times x minus 1. That expression is lambda squared. So we know that e of x times x minus 1, if we multiply the x times x minus 1, that's e of the quantity x squared minus x. That's equal to lambda squared, right? Now, if we do the expectation, expectation has this so-called linearity property. And remember when we talked about the variance stuff, expectation also has linearity property. So if I take e of something, x squared plus, well, let me just do the real one, minus x, that's the same as saying e of x squared minus e of x, right? That's exactly the linearity principle applied to expectation. So if I know this is equal to that, just by linearity of expectation, and I already solved for the Poisson, this is equal to lambda squared, well, all I need to do is take this quantity, that expression, equate it with this expression, and just do a little bit of algebra, right? So if I say e of x squared minus e of x is equal to lambda squared, I add e of x to both sides of equality, and what I get is e of x squared is equal to e of x plus lambda squared. Okay. So that means anywhere I see e of x squared, I can just replace it with e of x, which I already know is lambda from before, and then add a lambda squared to it. Okay? So going back to, everyone understand that step? Yeah? So going back to the variance equation, I already know e of x is lambda, and here I have e of x quantity squared, so that's a lambda squared. And this e of x squared, well, from that easier to solve problem, I know e of x squared is just e of x plus lambda squared. E of x, I know, is just lambda. So the variance of x for Poisson is just lambda, that's my e of x, plus lambda squared, because that's what this manipulation told me. And then I had that other part minus lambda squared, right? So the lambda squared minus lambda squared cancels, goes to 0, and I'm left with the variance of a Poisson is just equal to lambda, okay? Any questions about this? Does that make sense? Okay, and so what the result is, no questions? Yes. Yes, for the Poisson, but that's not the case for other distributions. It's the one weird one where that happens. Okay. Any other questions? So it kind of makes it easy, right? It's just the rate. And if you think about it, if the average number of events you observe is lambda, lambda is also the rate, which is the average number of events you observe per unit time, right? So it kind of makes intuitive sense. And the variability, how much does it differ? It can differ by the average amount that you see. So you see some rate, it can go up by the average or down by the average. So the intuition kind of makes a little bit of sense, but you still need to prove it. And for every distribution, when you have something you think is a probability, you have to show that it obeys the law of total probability, the sum of all the probabilities equals 1. And then you have to show the summary statistics, what the mean and the variance are. Once you have the mean and the variance, now you have these really short summaries that you can use to make great comparisons without having to describe all the different possibilities that your probability can produce. Okay? All right. No other questions? All right. So we have that result, and we did the fix up. And so I'm basically long way doing the same thing. And so we redo this e of x times x minus 1. That's e of x squared minus e of x. And then we do a little bit of algebra. We get e of x squared is equal to lambda squared plus lambda. And then we plug that in to the variance equation. The lambda squared and the minus lambda squared cancel, and we're left with lambda. Okay. All right. So if there are no other questions, um, I'll end there. That's all I had for today. But the big takeaway here is that it's really just the basic properties and algebraic manipulations through every single step, and the plugging in of definitions here and there, and then substitutions based on the Maclaurin series. And when you get an expression, the name of the game is trying to manipulate that expression to look like a pattern that allows you to do a reduction. And that reduction was trying to get it to look like a Maclaurin series. And it just so happens the Maclaurin for e to the x doesn't have a derivative term. The derivative term is 0 on each term for e to the x. Okay? All right. No last questions? Any last questions? So for something like this, I mean, I will stay up tonight and make sure I get the screencast posted, but please uh, get comfortable doing the algebra yourself, right? Don't just view it passively, actually get a pencil and paper or pen and paper, whiteboard or whatever, and just like get that muscle memory, if you will, of recognizing the patterns and knowing how to do these manipulations. It really is just practice, okay? All right. So with that, I will see you all on Monday. And the Poisson is one of the few distributions, not the only, but one of the few distributions where the mean and the variance are the same. They're both lambda. Okay. All right. And so we saw that the Poisson is nothing more than what's called the large sample result for the binomial. It's a funky binomial distribution where the number of trials n is infinite. And you can think of it as flipping a coin at every moment in time. And that coin comes up heads or success whenever you observe an event, right? And so a lot of these distributions you'll find kind of fold in on one another. They're all related because they all belong to something called the regular exponential family. And they all involve some kind of e to some quantity, and you can reduce them all to one another, which is beyond the scope of this class. Okay, so if no other questions, then I'll end there. That's all I had to say, and I will see you all on Monday. Please make sure you go over the Khan Academy. It's award-winning across the board, but specifically pertaining to this class, their modules on Taylor series and Maclaurin series. It's very, very well done. Okay? All right. So with that, I'll end there, and I will see you all on Tuesday.